2 new clean pages, right? Vocab needs to go on the left-hand side. Fold it over so we can see the terms not deficient. Push it up to the top of that left-hand side when you tape it in. Tape it down. All right, then on the right side of the page, I've divided it so I have 3 sections here. Doesn't have to be perfect. It's whatever your OCD requires. But just draw lines across to separate those 3 sections because we're going to give ourselves an example of each type of energy transfer, and then we're going to give ourselves an example of greenhouse effect. Yep, just draw a line across. It doesn't have to be super beautiful or anything like that. All right, so let's go through our vocab terms, starting with radiation. So if you read for me, prizes are still sitting there on the table. You can go ahead and help yourself choose a prize. Radiation, please read the definition of radiation for us. April. Electromagnetic. Big word there, electromagnetic. We don't normally think of energy in that form because we can't really use it in that form. So electromagnetic waves, that's how energy gets from the sun to the earth. It would not be able to travel from the sun to the earth otherwise. So remember how we talked about thermosphere and we said thermo means hot, and we're looking at those particles and how they've got a lot of energy and where are they getting that energy from? It doesn't seem like they have a whole lot of energy or it's hot out there, but it's just because they're really spread out. Well, that's the radiation, that's the electromagnetic waves that they're getting that energy from. That's the only way that the energy can travel across space because there's no other substance in order to transfer that energy. So we're going to see these other 2 modes of energy transfer has to have something, some substance or some way for that energy to be transferred. Electromagnetic radiation, because it's so far away from the Earth, because the particles are so spread out, it has to travel in that form in order to get to the Earth. So on the opposite side, that very top section right there, we're going to give ourselves a diagram to help us remember electromagnetic radiation. Oh, and radiation. Electromagnetic waves and radiation. So, radiation, I've got the sun, I've got the earth. We've got to get this energy to move across space. And so my little wiggly lines here that I know that I wouldn't remember what they were, so I labeled them, represent electromagnetic waves. So on that top line, that top section, give yourself a diagram. You can take up that whole section, because that's the only thing we're going to put in on the top section on the right-hand side. So sun and earth. And because of the fact that radiation is the energy that's traveling across space, so I labeled for myself that we've got this energy that's moving across space. Because I knew that I wouldn't remember what these little wiggly lines are, I labeled them electromagnetic waves. And then I put a little dude out there on the earth. He's very tall. All right, then grab yourself a highlighter, highlight the term radiation, and then box in your diagram that represents radiation. All right, next, conduction. Kale, would you read for us the definition of conduction? All right, and remember, if you read, feel free to help yourself to a piece of candy. So, conduction, the key to conduction is there has to be objects that are touching. There must be contact for conduction. Type of heat energy when objects contact another. So you come into class and you put your hand down on the table, and initially the table feels what? Cold. But if you leave your hand there long enough, and then maybe you move away and then you come back to it, what does the table feel like? Feels warm where your hand was at, right? That's conduction. The heat moved from your hand to the atoms in the table, but it had to be from you touching that table. Opposite can be true. We've got some drinks in here. You have a cold drink. You lay a cold drink on the table. Move the drink. How does the table feel? Feels colder, right? So what happened there? All right, so heat is always the one that's moving from where we have higher heat to lower heat. So the heat from the table moved and heated up, and that's why if you leave it there long enough, the ambient temperature, the air around it, the table that it's on, is going to heat up your drink. So it's absorbing heat from the table, and it's leaving the table colder than what was when you put the drink down there. But the key here is we have to have contact for conduction. So I have an awesome diagram here. So I went ahead and labeled it just in case I come back to it and don't understand what I drew. The hand is touching the stove. So nice hot burners on the stove. Dude's saying ouch, obviously, because that touch is conducting heat from the stove to his hand. Conduction requires contact. Radiation requires electromagnetic waves. Take a different color highlighter, highlight the vocab term conduction, box in your diagram for conduction. Grab a vocab sheet off the back table there. All right, finally we have convection. Read for us the definition of convection, please. Alex. All right, so fluid. And even before we get to that, so convection. Have we heard that term before? Yes, we have. And you bright, brilliant environmental science students, even though it's very early in the morning, I would bet that you already know what we're going to draw in this section. What are we going to draw? Don't let me down. Pardon? We used convection before in molten rock, yes. What did we draw to represent convection? And there was movement. There was things going up and things going down. Pardon? The arrows, the two arrows. So we had the red arrows going up and the blue arrows going down to represent convection. So, yeah, arrows. Hot fluids rise, so that's our red arrow going up. Cool fluids sink. I got purple, but you know what that means. Yep, and fold it over so that we see the... Say it again. Oh, is there none left in that little bag? There's got to be one somewhere. Okay, so hang on, I'll get you some. Oh, that's probably the bag that's supposed to go there. Here, use that one for now, and we'll fix it. Yep. I have some really expensive Kleenex over there by the phone in the corner. Uh-huh. So in the vocab definition, it talked about movement of fluids. A lot of times when we think of fluids, we think of liquid, but fluid is simply something that flows. So gases are fluids. Gases can flow from one area to another. Hot air rises, cool air sinks. Gases are fluids, so it's going to flow. When we looked at convection currents in the asthenosphere, the molten rock was a fluid because it's able to flow. The hot material rises, the cool material sinks. So fluids, and that applies to water too. So we're going to look at ocean currents in a few days, but that's going to happen in the ocean as well. Hot water rises, cool water sinks. So that's fine, but fluid is not limited to liquids. Fluids are things that flow. All right, next, greenhouse effect. Read for us the definition of greenhouse effect, please. Riley. Infrared. Okay, lots of big words in that too, but chances are you've heard of the greenhouse effect before, right? What's your general overall, when I say greenhouse effect, what comes to mind? Say it again. Plants, okay. Say it again. The lighthouse? How come? Oh, okay. All right. Well, I'm going to have to change that just a little bit then. I thought maybe there was another connection to it. All right, so we said plants, greenhouse plants. Why do plants need a greenhouse? Yes, and why does the plants need the greenhouse? Keeps them humid, keeps them warm. What did you say? And it'll use the sunlight in order to maintain the temperature inside the greenhouse. So like right now, when it's almost October and 105 degrees out, we don't need a greenhouse right now. But in the Oklahoma winter, and we'll see why Oklahoma winters can get to negative 20 degrees below zero, when it's super cold out, plants require that to maintain that temperature because they can't continue to grow when it's below freezing out. So you put them in the greenhouse then because the sunlight can get in to the greenhouse and it's going to hit the surface and heat the surface, which then heats the air, which then keeps the greenhouse heated so the plants can survive in there. And that's great. When you think of the greenhouse effect in terms of the planet, do you think of it as a good thing or a bad thing? Why would it be a good thing? Lighthouse. Okay, so generally speaking, nowadays when we hear the term greenhouse effect, we think of it as being bad. The thing is that if there were no greenhouse effect at all, then the surface of the earth would be too cold to maintain life. So we wouldn't exist without some level of the greenhouse effect. The thing is, and the reason why we think of it as being bad nowadays, is because we've kind of manipulated the greenhouse effect just a little bit. So the gases that it talks about, water vapor and carbon dioxide, those kind of gases, and remember we said this, less than 1% of the total composition of our atmosphere, but that means any increase to it ends up being a huge increase, ends up having a big effect. So imagine this. So you're at home, you want to heat up your meal. You've got it in a bowl. You put a piece of plastic wrap over it, right? Put it in the microwave, beep, boop, boop. It's done. You take it out. When you open up that plastic, or I got to take a step back. I'm getting too excited. So when you take it out, before you open up that plastic wrap, it's really not hot above it, right? I mean, the bowl's hot, but the air above it isn't necessarily hot. But when you open up that plastic wrap and you let all that trapped steam out, then it gets really hot. Does that make sense? Can you relate? Do you understand what I mean? Have we used microwave and heated stuff up before? That makes sense to you? Okay. I just want to make sure we're on the same page. So the thing is that's essentially a little microcosm greenhouse effect. The microwave energy can get in and heat your food, but whenever the food heats up, the steam can't get out because the plastic wrap is trapping it there. So these gases in our atmosphere are acting like a layer of plastic wrap. One layer is not that bad. We need to maintain a certain amount of temperature down here at the surface of the earth. The thing is that if we add any water vapor, if we add any carbon dioxide, we're adding multiple layers of that plastic wrap on there. And so now more energy can get in and less heat can get out, and more energy can get in and less heat can get out. And that's to the point to where you're opening up that plastic wrap and it scalds you or it burns you because there's so much heat that's trapped in there. So the greenhouse effect is essentially plastic wrap out there, those gases that are allowing sun's energy in, and it hits the ground, warms the ground warms the air there, then the air is going to circulate through convection, and it warms it up down here. But if it hits those water vapor, if it hits that carbon dioxide, that bounces it, it re-radiates it, it bounces it back down to Earth. What we need to do is if we have an excess amount of heat that builds up down here, we want some of it to dissipate out into space. Because the next day, the sun's going to rise again, and we're going to have more heat here. So we want some of it to dissipate. But if it's trapped, and it stays here, and then the next day the sun rises and adds more heat to it. And it stays trapped, and the next day we add more heat to it. So the greenhouse effect essentially is like adding additional layers of plastic wrap to keep more heat trapped down here at the surface. All right, so this diagram is going to go on the left-hand side underneath your vocab. So we had a spot. Whoops. Need the other one. So we had our vocab page. We had our vocab page taped in on the left-hand side, and we've got this spot underneath it. So that's where we're going to put this last little diagram. So here is my greenhouse effect. So I've got the Earth. I've got the sun. All of that energy from the sun can go through those greenhouse gases. Some of it gets bounced up, but the more greenhouse gases that we have, the more it gets bounced back down to Earth, gets reflected back down to Earth. Greenhouse gases.